Hello. Sorry, I'm back. I just couldn't. I've got like a time limit of 30 minutes for each of my videos, and that one was getting pretty close. So I decided to cut it off, and you guys can go take a break, um, and then come back to this one. But in any case, we're almost done here. We were talking about the sums of these convergent infinite geometric series, right? And we said, oh, okay, that's any series where the absolute value of r is less than 1, where it's, in other words, either a positive or a negative decimal or fraction, less than 1. Okay? So, for example, negative 1/3 would be convergent, positive 2/3 would be convergent, 0.3 and negative 0.3 would both be convergent, because when you take the absolute values of those, we get something that's less than 1, right? So anytime you've got, common ratios that look like this, it's going to be convergent, right? And we saw the effect of that with Zeno's series, because if you multiply by a number that's less than 1 by a fraction, it causes the terms of the series to get smaller and smaller and smaller, and so that they add up. As they add up, they tend to track towards a particular value, like a Zeno series did. So anyway, so if we know it's convergent, all right, then we've got this formula here for the sum of the series, and it's a super easy one, right? Where a sub 1 is the first term in the series and r is the common ratio. Notice there's no place here for n, the number of terms in the series, because with an infinite series there is no n. The series is visualized as you just keep going forever, right? So let's start with Zeno's series that we worked with here. 1 plus 1/2 plus 1/4 plus 1/8 plus ... all the way down to infinity, right? So what does when we actually added those up, like on our calculator, kind of by hand, we saw that it tended to get closer and closer to 1. Let's see what this formula shows us. Okay, so S sub n, I'm going to say S infinity, is equal to the first, Zeno started with, now I forget, did we start with 1 or did we start with 1/2? We started with 1/2, didn't we? With Zeno's. Right, so we're going to start with 1/2. Sometimes the series starts with 1. We're going to start with 1/2, 1/4 plus 1/8, and so on. Well, we saw that r was equal to 1/2, right? And the first term is 1/2. So, using this formula, 1/2 divided by 1 minus 1/2, that's 1/2 divided by 1/2. Why, that's 1. Okay? That's that strange that's that limit. Now you're going, but Mr. Waters, I thought what we showed was that it got closer and closer and closer to 1, but it never actually got there. And that's true if you're thinking in terms of a finite number of terms, right? But if we imagine in our heads that series keeps going on forever, then the limit of that series was 1, so it turns out that the sum is equal to 1. Now, okay, we'll come back to an example of that in a minute, of that strangeness in a minute, right? So let's see here. Let's try this infinite series. Let's say we've got the infinite series 5 plus 5/2 plus 5/4 plus 5/8 plus ... and it just keeps going. That ... means it just keeps going. Now you're thinking, that doesn't even look like a series, right? Well, okay, it really is. It doesn't even look like a geometric series, but we can prove it. Notice this one, they've got 2, 4, 8. This one has got 1 on the bottom. So notice 1, 2, 4, 8. So we seem to have this multiplication effect, but in the denominator. So anyway, let's use our calculator here to figure out what R is and to confirm that this is actually a geometric series. Okay, so I'm going to divide 5 over 2 divided by 5. I'm going to divide 5 over 2 by 5 over 4. So, according to Mr. Calculator, 5 over 2 divided by 5, that's 1/2. And 5 over 2, or 5 over 2, or, oops, I wrote that backwards. 5 over 4 should be that one on top, that one on the bottom. 5 over 4, you're going to see, you divide those, that also works out to be 1/2, okay? So here again, the common ratio is 1/2, and then the first term, though, is equal to 5. So if you want to, you can just get your calculator out and see what happens, see if this approaches a limit, but we'll go ahead, we're going to find the sum of that series, okay? This is example 2, by the way, example 1, okay? So this is, the sum is, using our formula up here, 5 divided by 1 minus 1/2. So that's 5 divided by 1/2. Divide those, that's 10. So if you're to add these over and over, keep adding more and more and more terms. 5 over 16, 5 over 32, 5 over 64, and so on, the number would start out not very close to 10, but would get closer and closer and closer. This would be 5, then 7.5, right? And then like 8.75, and so on. It wouldn't start out close to 10, but would it get closer and closer and closer and closer? And as these fraction terms, as the terms got smaller and smaller and smaller, it would inch closer and closer and closer to 10, but more slowly, okay? So that sum is equal to 10. All righty? Very good. Okay, so that's kind of how that goes. Now let's try one more of these, actually 2 more, okay? So example 3, let's try this series, 4 minus 1 plus 1/4 minus 1/16 dot, dot, dot. Now you're thinking again, Mr. Waters, I don't even see that as a geometric series, but let's see how. Okay, let's see here. Each subsequent term by the previous term, -1 divided by 4 is, of course, -1/4, right? And then 1/4 divided by -1, oh, look, that's -1/4 again. Or -1/16 divided by -1/4, or -1/16 divided by -1/4. Oh, they're all equal to -1/4. So R is equal to -1/4. Now, is that convergent? Yeah, because we take the absolute value of -1/4. Why, that's equal to 1/4 less than 1. So it converges. So to find the sum of that series, S is, remember the sum of the series was A1 over R minus, over 1 minus R, okay? Okay, so the first term is +4, and then 1 minus -1/4, right? Because we have to use the R there, it's minus negative, so that's 4 divided by 5 over 4, if we add those fraction-wise. And to simplify that, we multiply by the reciprocal, right? And we get 16 over 5 would be the sum of that convergent series. Okay, so the only infinite series that have sums are these convergent series. Now, these have got a lot of uses. In higher math, these infinite series have got many, many useful applications, although it'll be a while before you get to them again. But one place we've seen it all the time, a lot, is this. And this is going to be example 4. 0.5 bar. And as you know, taught back in arithmetic, that meant 0.5 repeating forever, right? Well, can you see that's actually an infinite geometric series? Because that starts out as 0.5 plus 0.05 plus 0.005 plus 0.0005 plus 0.00005. We keep adding one more zero, right? And then it keeps going forever. So these repeating decimals are actually infinite geometric series. Well, what's the R value? And do they converge? Well, let's see. R is going to be equal to each following term by the term before. So it's going to be 0.05 divided by 0.5 or 0.005 divided by 0.05, right? And you can see, well, that's equal to 0.1, isn't it, right? Right? P equal to 0.1. So it's a convergent series because, as you can see, that common ratio is less than 1. So what's the sum of it, I wonder? Well, the first term is 0.5 divided by 1 minus 0.1, right? That's 0.5, and 1 minus 0.1 is 0.9. So that's 0.5 over 0.9, which actually simplifies to the fraction 5/9. So 0.5 repeating forever is equal to the fraction 5/9, right? Which is why we know that that's a rational number. Now you're thinking, but what? But you've seen that on your calculator all the time, right? You take 5, divide by 9, and what it tells you is, oh, look, 5 bar, 0.5 repeating bar right there, right? Or if you divided the bottom number into the top number, you know, it would keep going forever. Okay, does that make sense? Like that. And it would just keep going, going, and going, and going, and going, and going. So these repeating, this is one way of showing that these repeating decimals really are equal to an exact fraction. And it's also a way to figure out what that exact fraction is by finding the sum of the corresponding infinite geometric series. Okay? Alrighty, very good. So that's how that goes. All right, now I've put some, that's all I need to tell you about this. I have put some classwork up that's not due, but you could, if you want to get some extra practice in how this works, works before you try the homework, you should definitely do that. And remember, there's going to be a test coming up on this pretty soon. Stay tuned. Bye.